Welcome back, everybody. This is our third session in NEET previous year questions for class 12th of chapter Moving Charges and Magnetism. Before this video, we have made two videos in this series, and again, those videos are available on our channel's playlist section. We have also started similar series for JEE previous years. So if some of your friends are preparing for JEE or you want some additional practice, then you can also find those videos in the playlist section of our YouTube channel. And if you find this video useful, then do press the like button, share them, and subscribe to our channel. And also, if you want to donate us something, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. In the previous one, we solved around 90 or 20. So this was the last one. Let's move to the next. A beam of electron passes undeflected through mutually perpendicular electric and magnetic field. If the electric field is switched off, the same magnetic field is maintained. The electron moves. So here, initially, what we had initially, the beam was passing undeflected, means we can say as both electric and magnetic field were there, so electric force was balanced by the magnetic force. Suppose this is a charged particle, and on it we have upward electric force and it is balanced by the downward magnetic force, so it keeps on moving in a straight direction. Now if we remove electric force, then what will happen? We have a magnetic force acting on the particle and it will try to move it down. So now, due to this downward force, the particle will have two components of velocity, one in the horizontal and one in the downward vertical. And we know that magnetic force always act perpendicular to direction of velocity, so it will rotate it in a circular orbit. So particle will start moving like this. If velocity is directly perpendicular to velocity, velocity is directly perpendicular to magnetic field and their angle is 90 degree, then it will keep rotating in the form of circular. It will keep on rotating in circular form, and if velocity and magnetic field has some angle theta which is greater than 0 and less than 90, then its path will be something like this. Path will be circular, but motion will be in 2D. We will have the concept of pitch here. So in this case, we assume that angle is 90 degrees, so it will move in a circular orbit. So option A will be the right answer here. Moving to the next one. In a mass spectrometer for measuring masses of iron, the ions are initially accelerated by electric potential V and made to describe circular path of radius R using magnetic field B. If V and B are constant, the ratio charge and mass will be proportional to. So we have to find ratio of charge by mass, or Q by M we have to find out. This is the term we need to find out. Now, particles are accelerated by a electric potential, and when we accelerate some charged particle with the help of electric potential, then its kinetic energy half m v square, that is the kinetic energy acquired by the charged particle when it is accelerated by the potential v. So here you need to notice that capital V represents potential and small v represents velocity. So this is the relation between kinetic energy acquired and the potential applied with the charge also. It also energy depends also on the charge, that what is the amount of charge on the particle, on the charged particle we have. So here we are discussing regarding Here we don't have different type of charges, I think, or ions. So we assume that all of these have the same mass. So from this, and we have to find out charge by mass. So what we do here, we know that radius, when a charged particle enters in magnetic field, its radius is given by mv by qb, and we can write charge by mass from here, that q by m is equal to velocity by rp. So now we can find value for velocity from here. From here, velocity is 2qv, where capital V is potential, small v is velocity, divided by m under root, putting this value here. So we will have 1 by rp 2qv by m. So we can further rearrange it like this, that this is q by m. Now we can see from here that we have q by m here, and we also have q by m here in the form of under root. So what we do, we square both sides. Let's square them. So q square by m square is equal to 1 by r square b square 2qv by m. That q square get cancelled, that m is cancelled. So from here, q by m is equal to twice of v divided by 1 b square and r square. And it is asked that it is proportional to, so we can see that q by m is proportional to 1 by r square. So option A will be the right answer here. Moving to the next one. Charged particle moves through a magnetic field in a direction perpendicular to it. Then speed of the particle remain unchanged, direction remain unchanged, acceleration remain unchanged, velocity remain unchanged. So we know when velocity is perpendicular to magnetic field, then there is a force acting, that is magnetic force, and that is also perpendicular to the velocity. And in one of our previous video, we already discussed that work done by the magnetic force is zero. So change in kinetic energy is also zero. But as particle is rotating in a circular form, means here magnitude of velocity is not changing, but direction is changing. So if direction is changing, we will say velocity is changing, and if velocity is changing, then there is acceleration. So velocity is changing, and velocity is changing means acceleration is there, and acceleration is there, and we also know the direction is changing. So let's compare. Option B, direction of the particle remains unchanged. That is wrong. Direction changes. C, acceleration remain unchanged. So yes, acceleration is there. And velocity remains unchanged. That's again wrong. So coming to the point is, speed of the particle remain unchanged, and speed of the particle is equal to magnitude of the velocity, and magnitude of the velocity is unchanged. So speed of the particle is unchanged here. Moving to the next one. Charged particle of charge q and mass m enters perpendicularly in a magnetic field B. Kinetic energy of the particle is E, frequency of the rotation is. So we have to find out frequency of the rotation. Kinetic energy is given to be E. So we know that kinetic energy is just half mv square. So half mv square is equal to E. We have to find frequency of rotation, that we can find out from the time period. Time period is given by 2 pi m by QB, and frequency is inverse of time period, so frequency will be QB by 2 pi m, that is option B. And here we don't have we can say, if we had velocity here, then we could have formed this in the form of energy, but we don't have velocity here, it is independent of velocity. That's why we cannot substitute energy here by substituting some other terms. So option B will be the right answer. Moving to the next one. Current I flowing in a coil of area A, number of turns N, magnetic moment of the coil M is equal to. So we know that magnetic moment of a closed loop is equal to number of turns times current times area. So here we have N turns, small I current, and A area, that is option A. Moving to next one. 10 electron volt electron is circulating in a plane at right angle to the uniform electric field. Value of field is mentioned. The orbital radius we have to find out, and we know that orbital radius is r is equal to mv by qb. Mass of electron is 9.11 into 10 raised to power minus 31. But here we have given energy of the electron, and that energy is the kinetic energy, and we know that, suppose this is energy E, that is 10 electron volts, so 10 into 1.6 into 10 raised to power minus 19 joule. And we have a relation between momentum and energy. Momentum is given by under root 2 times m times of the energy, and here mass into velocity is the momentum, so we can directly use here 2me in place of momentum divided by qb. So it will become under root 2 into 9.11 into 10 raised to power minus 31 into energy, that is 1.6 into 10 raised to power minus 18 divided by charge, that is 1.6 into 10 raised to power minus 19 into field, that is 10 raised to power minus 4. Now solving this, what we will get? We will get 10.67 into 10 raised to power minus 2, and that is 11 centimeter. That is in meter, and 10 raised to power minus 2 will 11 centimeter. So option C will be the right answer here. Uniform magnetic field act at a right angle to the direction of motion of electron. As a result, electron move in circular orbit of radius 2 centimeter. If the speed of the electron is doubled, then the radius of the circular path will be. So we know that radius is given by mv by qb, and it is mentioned that speed is doubled. So if here velocity is doubled, then the radius will also get doubled, and as initial velocity, initial radius was 2 centimeter. So if we double the speed, radius will also double, so 2 into 2, 4 centimeter will be the right answer here. Moving to next one. We have two statements here. Biot-Savart law gives an expression for magnetic field strength of an infinitely small current element ideal of an current carrying conductor only. Second statement, Biot-Savart law is analogous to Coulomb's inverse square law of charge Q, with the former being related to field produced by a scalar source ideal, while the later being produced by the vector source Q. So here first statement is by default, hopefully everybody has known that in In the Biot-Savart law, we get magnetic field due to small current element at certain distance, and value of magnetic field is given by mu node I into I dl cross r by r cube. That's the value of magnetic field by Biot-Savart law. Here both of these are vectors. That's why we have r cube here in the denominator. So statement 1 is correct. But in the statement 2, it is mentioned that Biot-Savart law is due to ideal I into dl, that is scalar, so that's right. And Coulomb's law is due to vector source, that is charge. So, and we know that charge is not vector, charge is scalar, whereas here ideal actually is considered to be vector because we take direction in this length. So here ideal will be a vector form. So it is written in the inverse. Here ideal should be the vector and q should be the scalar. So statement 2 is wrong. So option C, that's 1 is correct and 2 is incorrect. Moving to the next one. A tightly wound 100 tons of coil. So N is 100. Radius is 10 centimeters. So 10 into 10 raised to power minus 2. Current is 7 ampere. The magnitude of magnetic field at the center of the coil. We have to find magnetic field at the center of the coil, and for that we know value is N times mu node I by twice of R, where N is the number of turns. So 100 4 pi into 10 raised to power minus 7 into 7 divided by twice 10 raised to power minus 1. So this will be 2 pi, and we have 14 pi into 10 raised to power minus 5 with plus 1 more, so 10 raised to power minus 4, and 14 into pi will be approximately equal to 43. We are just approximating here, into 10 raised to power minus 4, so it will be 4.3 into 10 raised to power minus 3. So 4.3 millitesla, that is near around option B for us. Moving to the next one. A very long conducting wire is bent in the semicircular shape from A to B as shown in the figure. Magnetic field at point P for steady state configuration will be given by. So we have to find magnetic field at point B. So let's divide this diagram into some parts so that we can deal them individually. Here we have a arc AB and a conductor, that is A and B. So let's say this is conductor AD and this is conductor B. Now we will have field due to three parts. So our total field will be due to conductor AD plus due to arc AB, that is arc AB, and then due to conductor BE. Now let's see the direction of magnetic field. Now using right hand screw rule, if you move your thumb towards the right direction, then you will find that magnetic field here in case of conductor AD will be coming from the top and going to the down. Means at point P, magnetic field will be going into the page. And for conductor BE, if we orient our thumb towards the left direction, here again magnetic field will be going into the page at point P. So both of these fields will be added. Now for the arc AB. For arc AB, if we orient our thumb towards the downward, from A to B, then we will find that magnetic field here at point P will be coming out of the page. Means if we take coming out of the page as positive, then these two fields will be negative, and due to arc, field will be positive, and due to these two conductors, field will be negative. So let's find out the value due to conductor. And as both of these conductors are identical, so their fields will be also identical. So BAD is equal to BE will be mu node by 4 pi into distance. That distance is r between point P and the conductors, into sine of angles, and here let me draw the angles. As this conductor is an infinite conductor, so this angle will be approximately 90 degree, because this is an infinite conductor. So here angle will be 90 degree, and here angle will be 0 degree. So we will get sine of 90 plus sine of 0. So it will be effectively mu node by 4 pi of the radius, and both of these fields will be equal, and both of these will be negative in the into the page direction, so negative k. And now coming to the arc. For arc, as we have only half of the portion of the loop, so magnetic field due to loop AB will be mu node I times by twice of the radius, and we have only 180 degree coverage, so 180 by 360, so it will be mu node, and we forgot current here, sorry, I will also be there, so mu node I by 4 R, and that will be out of the page. So total field will be field due to arc, that is positive, and field due to both of the conductors, that is negative. 4 pi r k, this is due to one conductor, and this is due to second conductor also. They will have the same field as they are identical. So now we can take mu node I by 4 r common. Here we will have 1, and from here we will have 1 by pi and 1 by pi, so 2 by pi, and here we will have k also common. And we know that 2 by pi is 2 by 3.14, means here denominator is bigger, and if denominator is bigger, then the whole ratio is smaller than 1, so 1 minus something smaller than will be positive terms, so total field will be out of the page, so that is pointing away from the page. Option A will be the right answer here. Moving to the next one. A long wire carrying a steady current is bent into a circular loop of one turn. Magnetic field at the center of the loop is B. It is then bent into circular coil of n turns. The magnetic field at the center of the coil of n turns will be. So we have to compare magnetic field of a loop and a coil. So let's first do for the loop. And here we will solve for coil. As length of wire is constant, so suppose for loop radius is RL, and for coil radius is RC. So 2 pi times RL should be equal to length of the wire, and here we have n turns, so n times 2 pi RC should be equal to length of the wire. So from this we can say RL is equal to L by 2 pi, and from here radius of coil is equal to L by 2n pi. Now magnetic field due to loop will be mu node I by twice of radius of loop, that is mu node I by 2L and 2 pi. Here we have it get cancelled, so it is mu node I pi by L. Now for the coil, magnetic field will, as we have n turns, so n times mu node I by Rc. So it will be n mu node, or twice of Rc, mu node I twice of L, and we have 2n pi here. So 2 get cancelled, and it is n square mu node I pi by L. And if we can see, this is value for magnetic field of loop. Mu node I pi by L is the magnetic field of the loop. So BC, magnetic field of the coil, is n square times magnetic field of the loop. And here it is mentioned in the question that magnetic field at the center of the loop is B. At center of the loop is denoted as B. So it at coil will be n square times B. So that is option B for us. Option B will be the right answer. Moving to next one. Here we have a wire carrying current I on the shape as shown in the figure. The linear parts of wire are very long and parallel to x-axis, while semicircular portion of the wire is in YZ plane. So magnetic field at point O. And this type of question we already solved here. And let me show you. So this was the question which we already solved. It was a similar one. So we will also do same here. So let's first find out the direction of the magnetic field. As for this conductor, let's name it. We have X, Y, Z as mentioned already. So suppose this conductor is A, B, and arc is B, C, D, and we have another conductor that is D, E. So for conductor AB, the current is going into the page, and here into the page direction is minus X direction. So if here current is going into the page, then on the right hand side, on this side of the conductor, magnetic field will be rotating using right hand screw rule like this. That magnetic field will be going into the page in the right hand side of the conductor, means at point O, magnetic field due to conductor AB is going downward. Now similarly, looking for conductor DE, using right hand screw rule, here current is coming out of the page, so magnetic field will be rotating like this. So again going into the page. So magnetic field due to conductor AB is in negative K direction, going down, and here downward direction is negative K direction. Let me also plot that. So downward direction is here negative K direction. So it is in minus K, and B of DE is also in minus K. Now for the arc BCD. Here current is moving in the Y direction. So if we see magnetic field at point O, it will be in the negative Z direction. Magnetic field will be something like this, and it is in negative Z direction. It is in negative Z direction. So magnetic field due to arc BCD will be in negative X direction. Sorry, let me clear it again if you have any doubt. It is BCD. Here current is flowing from here current is flowing in the Y direction, And if we look at the direction of the current in the y direction and using right hand screw rule, we will find the direction of the magnetic field. It will be coming from the back of the loop and going at point O into the loop from the downward. So here magnetic field will be in the negative z direction, so it is negative I. Now let's find out the magnitudes of the field. So magnitude of the field for conductor AB and ED will be same, and it is given by magnitude will be BAB is equal to BED magnitude wise, and that will be mu node I by 4 pi. The distance here is R into sine of phi, that will be 1, sine 90 plus sine 0, that will be 0, so it will be mu node I by 4 pi R. And now due to loop, as it is semicircular loop, only half portion we have, so magnetic field due to loop, or we can say arc BCD, will be mu node I by twice of R into 180 by 360, so it will be mu node I by 4R. So now let's write the total field. So total field will be due to these two conductors, and this is in negative k direction, so their total field will be twice of this value, twice of mu node I by 4 pi R with negative k direction. And due to semicircular loop, we have field in negative x direction, so negative mu node I by 4R of I. So total field will be, if we take negative common, and mu node I by 4 pi R common we have to take. So it will be twice of k, and negative is taken common, so we have plus here, and pi is also taken common, so we will have pi here, pi of I. So that is our option A. So option A will be the right answer here. So with this, we end this video here. Hopefully what we have covered is helpful to you. Again, if you have any doubts or suggestion, you can put them in comment section. I will try to resolve or implement. If you find this video useful, then do press the like button, share it, and subscribe to our channel. And if you like to donate us something, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.